Over the years, there have been a lot of unanswered questions about electric current. That is, what is the major difference between flowing electron and current? In this video, we will be looking at them. The way electron and conventional current flows will be looked at. Without any further ado, let's get started. Mathematically, current can be gotten when voltage is divided by resistance, or electric power can be said to be the multiplication of current and voltage. In a layman's terms, we are looking at how electrons behave in a conducting material. That is because current is the movement of free charged particles under the influence of force.
These charged particles could sometimes be known as free electrons, while the force can be known as the voltage acting on the material at a point in time. While assuming that there are no resistance that tends to impede the flow of the current.
To further look at it from another perspective, we have two materials here. One material can be termed as a conductor, which is made of copper, while the other material is made of wood. Now when I break this copper material into smaller pieces, and when I take a tiny piece here for observation, looking at this copper atom here, we can see that at the center of the atom, there is a nucleus. This nucleus consists of electrically positive protons and neutrons which are electrically neutral.
At the center of that atom there, those protons and neutrons are held in the nucleus by the strongest of known fundamental forces that is known by human measurements. Again, it can be said that the nucleus seen at the center of the atom makes up much less than 0.1% of the volume of the atom. So yeah, we will need a great deal of magnification here.
Now, around this nucleus, there are different orbits, and the electron usually revolves around the orbits. As the electron evolves, the nucleus will also be accumulated by protons and thus become positively charged. Now, due to the unlike terms, that is because the electron is negatively charged and the proton is positively charged, there is going to be a force of attraction between them. Now, because we are considering a copper atom, this material has an atomic number of 29.
That is to say, the copper atom has 29 electrons and 29 protons. Or let's say, the electron number usually equals the number of protons in any atom.
So at the center here, the nucleus will consist of 29 protons, while the 29 electrons here will get themselves arranged within these orbits. As we can see on the fourth orbit, we are only having one electron.
Again, the arrangements of those electrons within the orbits is done using this formula here. That is 2n square. Mathematically, this denotes the results of multiplying the number n by itself, and then the product multiplied by 2. That is, 2 multiplied by n raised to the power of 2. For example, the third orbit can be calculated like this. 2 times 3 raised to the power of 2. That should be 2 multiplied by 9. This will equal to 18.
Now, the electrons in the orbits that are closer to the nucleus tend to have a strong force of attraction. This force of attraction is due to its negative charge value, and it will be very difficult for the electron in this orbit to move freely within the orbit, or have the mobility to move to another atom. However, the electron on the fourth orbit has a lesser force of attraction. This is because the orbit is a bit further away from the nucleus. Hence, the force experienced by this electron on the fourth orbit is less or nothing. So this electron at the outer orbit of these copper atoms is free to move, and it can also eject to another atom. This electron can also be called less free electrons.
Similarly, the same calculation can be carried out on an aluminum material. Since an aluminum material has 13 atomic numbers, then here we will be having 3 free electrons at the outermost orbits of this atom. This electron will also exhibit the same characteristics that copper has, just that copper has lesser resistance and more current conductivity than aluminum.
Wood, on the other hand, also comprises of electrons and protons, but it lacks the presence of neutrons. This neutron is a key player here. That is because the neutron is directly involved in the way electrons spin within the orbits. This lack of neutrons nullifies the directional charge that would have been experienced by the electrons when the material is brought into a magnetic field. Hence the reason why wood is a good insulator, as no orbital movements of electrons are possible within the atom. So any material that has weight and can also occupy a space is known as matter. And of course, an atom is a tiny particle that a matter is made of.
So in a copper conductor, there are trillions of atoms present within this conductor. Even the tiny pieces you hold there consist of as many atoms present within.
So in this material here, we will have trillions of electrons moving in random directions at intervals, whereas in this insulating material here, the electrons are tightly held here. Now, we will need a force that will cause the random moving electron to move in a specified direction.
Now, when a voltage is applied here, this will cause the random moving electron to move in a particular direction.
Or we can say that, when a conductor is brought into a magnetic field, an induced current will be generated in the connected circuit.
Now when we relate it to electricity, then we can say that there are 2 types of flow: the conventional current flow and the electron flow. To further understand how these 2 works, let's look at the experiment that Benjamin Franklin carried out. During one of its scientific works, Benjamin rubbed a glass tube with a cloth, and after rubbing the tube, there was a buildup of electric charge. Today this charge is known as static electricity. At that time when he was conducting the experiments, someone mistakenly touches the glass tube. Immediately a little shock was felt by that individual, as at that time, Franklin believed the glass tube to be positively charged, and the person touching the tube to be negatively charged. So Franklin's statement afterward was that the generated charge must have flown from the glass to the person. This flow of charge is what is now known as conventional current flow. In 1897, Joseph Thomson, during one of his cathode ray experiments, he discovered that an invisible particle was moving inside a wire. And when the conductor is energized, the particles begin to move in a specified direction. The irony is that the moving particles, when energized, tend to move towards the north poles. And as such, the movements can be said to be from negative to positive. This particle is what is now known as electron. Of course, electrons are said to be negative. So when we looked at Thomson's experiments here, then we can say that when that charged Franklin glass was touched, the negatively charged electron was actually flowing from the person to the glass, not the other way round.
That said, we can say during electricity flows, electron will move from negative to positive, and the conventional current flow is from positive to negative.
Mathematically, current can be represented using these differential equations. That is, current equal to the change in the charge over the unit time. This can further be represented as the ratio of coulombs and time. And the time is in seconds. This will equal to the amp or the amount of current flowing at that point in time.
So 1 amps can be said to be 1 coulombs per second, where 1 coulomb of charge is equal to 6.24 times 10 raised to power 18 of unit charge of an electron. Of course, don't forget that electrons are negatively charged.
Now, in order to calculate the amount of charge flowing within the circuit, then the integration of this mathematical equation will equal to the integral of flowing currents multiplied by the dt, when it is integrated from 0 to t.
With all these, we can be able to deduce why there is an instant power supply, even when a circuit is powered at a great distance. People believe that current usually flows from the generating station to the load.
Don't forget that earlier on, when we were looking at electrons in the atomic orbit, we said the electron in a conductor usually moves in random. However, when an applied force is connected, this will cause the random moving electron to move in a defined direction. So when a circuit is connected to a source, the electron of the circuit flows in the direction of the source.
Again, the real thing that moves should be the magnetic field. When connected to a live source, the magnetic field that causes the electron to move in that direction will be transferred to the new circuit, thereby causing the random electron to move in a specified direction too. This is why every conductor that carries currents usually has a magnetic field around itself. And that is it on today's series. I hope you have learned something new today. See you at the next one.